Lab Guy here. I thought I'd bang out a quick video for you today. Work has begun on the 10.4 Eleanor RGBY NBTV signal generator. I've begun assembly and construction of the primary circuit board. The first part was to finish the schematics, which I did, and then perform an initial parts placement, which I did by using the sockets themselves on a large piece of board to figure out exactly how to get them into the smallest possible area. In the end, I was able to fit all 28 chips onto a 4 by 5 inch protoboard. So it's not very big at all. You'll see that shortly. This is the parts placement of the board, the parts locations. So it laid out quite nicely and logically, in fact. It flows left to right. It came out very well. I'm very pleased with the layout. So at the current moment, this is what the board itself looks like, but we'll get into that more in a moment as well. So I thought you'd be happy to see a video this morning, and I'm pleased to bring you one this afternoon, evening, if you have such things on your planet. And yeah, what else can I say? The project is out of the starting gate and galloping down the track. Now let's hope we don't break a leg. I'm going to install the 7805 voltage regulator right here on the board, which will be right here. I have the regulators ready to go, but I suppose I better go get a heat sink. I suppose standing up is okay. Kind of evil, doesn't it? I think we can put it there. What's that, Lab Guy? This is heat sink compound. I keep it in this bag because it's messy stuff. It likes to get on everything. Take a dab, a little dab will do ya. Put it on your heat component. Spread it the thin layer. Try not to get it everywhere, which it likes to do. Put the messy stuff away again. I keep it double bagged so it doesn't contaminate everything in the bin. There we go. Alright, our transistor is buttered up. We'll clean our heat sink. I don't think this circuit's going to run very hot. I'm using all CMOS parts, so current consumption should be low. Alright. And when I mount the fins, I want them hanging over the edge of the board so that air can circulate over them. If I place it inside the board, no air can come up from below. And hanging over the edge, but it is sticking out quite a ways. So I believe I have to bring it in. Also, the heat sink is taller than our standoffs. The standoffs prevent the parts from getting beat to death as you work on the board. This is a very easy thing to fix. I put these standoffs on my boards to support the board during construction. And if they're too short, clearly we just add some more. Like it's a 4-poster bed, then when you flip the board upside down, it's not lying on the table on its parts. So now these standoffs now hold the board up off the table. Spread the pins on the part just a little so that he doesn't fall out when I flip him over like that. Time to solder him down. So when I install a part like this, I solder one pin only. Then I can straighten the part so that it is cosmetically attractive. The electrons care? Not really. Do the people who look at the project care? Oh yes. They can be quite vain. And that's good. Yeah, perfect. And now we solder the other 2 pins. Alrighty. I don't cut them completely flat to the board, but I do cut them short. And then we have our part in place. Good. And then, oh yes, should have done that. Oh, and our heat sink is not level. That's alright, we can straighten that later. So the next thing is to solder the center pin of this device to the ground plane itself, the same way that the ground pins of all of these sockets have been soldered. You can see the little solder spots around them where they've been grounded. I've gone through and grounded every single socket and put in the power supply bypass capacitors, the 100 nanofarads, at every single power pin on every socket before we even start. I've outlined all the parts on the back of the board so that they are visible, so that as I wire them, I hit the right rows and the right pins. Very important, you know. the 10-4 Eleanor. She's going to be a beauty. So first we ground the center pin of the regulator, then we will add his bypass capacitors. Now doing this, it helps tilt the board up for me. Very good. Don't know if you can see it, but that center pin is now soldered to the ground plane. The old adage of keep your wires short is a religion here. So the lead from the regulator chip to the board for ground is about as short as is physically possible, short of bolting the heatsink tab, which is also ground, right to the ground plane, which I also do on occasion. I just felt that it needed an aesthetic, a little asymmetry to offset the regularity. That did lay out. The placement is what it's officially called. The layout came out extremely well. We'll go into the circuit sections in a little bit. Let's finish this regulator. Alright, so the next thing I need to do is add capacitors. So what I like to do is put a 10 microfarad bypass capacitor on each pin, and I keep all my capacitors numbered for just such an occasion, such as this. These are 10 microfarad 25 volt non-polarized capacitors, and they're about the size of a large grain of rice. They take up very little room as compared to their electrolytic equivalents. They do have a pretty high tolerance. They can be anywhere from 6 to 14 microfarads, and I've noticed that high tolerance components are usually on the high side. So if you want a 10 microfarad capacitor, you're guaranteed essentially, I don't know about guaranteed, but essentially you'll get at least 10 microfarads. So if you're doing timing circuits, measure your capacitor with a meter first and calculate based on the very real value you got for that particular capacitor, and you can't go wrong. Alright. There's plenty more where he came from. Keep my surface mount caps, bypass capacitors, in one of these jars that I used to buy cashews. You may have noticed I've lost a little bit of weight. Yes, I don't buy cashews anymore, among 100 other things I don't eat anymore. Alrighty then. So I will be installing these on the bottom, right across the pins. There's 3 pins in a row. The 2 outside pins are the input and output, and the center is the ground, so I will solder the capacitors right across the pins. Keeping those leads short is a religion at Lab Guy's World. There's one. Turn it around so that I can come in from the other direction. Not sure you'll be able to see them, but the 210 microfarads are right there. So that's how much room a 5-volt regulator takes up on my board. 3 pins. Now if you're one of those people who likes the high frequency bypassing as well, we could add a pair of point ones on there in parallel with them as well, which I may as well do at this point, having mentioned it. Same principle, same procedure. So I get the point ones, 0603. That's 60 mils long and 30 mils wide. They fit between the solder pads on this breadboard. So it's like this breadboard's laid out for brick laying, as I call it, these kind of parts. There we go. Put that out of the way. So these guys are really tiny. Very, very tiny. And just push it in there. So now we have a 5-volt regulator with 2 input bypass capacitors, a 10 mic and a 100 nanofarad, and 2 output capacitors of the same values. So on this board, the 5-volt regulator takes up the space of 3 pins. 3 pins! Isn't that amazing? With these parts, with this regulator, the order of the signals going from left to right across from the front view is input, ground, output. So we'll go ahead and begin wiring up our positive 5 volts from this chip to all of these chips except these 2 over here, which are our output op amps. They get wired later to plus and minus 12 volts. I keep all my wires color-coded for just such an occasion. I like this bowl because it looks like a pride parade. So for my color codes on my boards, black wires are ground wires, red wires are +5, green wires are -5 volts, orange is +12 or +15 depending on the project, and violet is -12 or -15 depending on the project. And I use yellow wire for all signal interconnections. This makes it easy to prevent soldering a signal wire to a power line by accident and then sending voltage out one of your jacks and burning up your DVD player or your earphone or whatever. So let's get on putting on the 5 volts. Eventually, I'm thinking, I just started using this little tub today, I'm thinking of running a bolt through these so that I can pull the wire from within the tub and keep them all in one place. What do you guys think of that? Leave a comment. But for now, we'll just remove the spool as needed. Here we go. Alright, now you see where these standoffs come in handy. You see how it's taller than the heatsink? Now when I flip the board over, I don't bend that heatsink all to hell. Pretty clever, eh? These are called hermaphrodite standoffs. I use American 440 gauge, and what it means is that they have a female opening on one end and a male threaded protrusion on the other, so that you can stick these together and make a long stick out of them. Very useful. Okay, so most of these chips are running on 5 volts, as I mentioned, and what I'm going to do is, if you look, they're arranged relatively in rows and columns. So I'm going to run power lines up to the top edge of the board and then interconnect them at the top edge of the board, and essentially, for the most part, tie the regulator in at the middle of the upper run so that it branches out like a Y, and then down the legs to the various chips. This power line will not be heavily loaded. Even at full power, it's probably only 100 milliamps. I'd be surprised if it's that high. It might be, I don't know. I haven't calculated it. I'm using 74 HC family parts. The flash memories are CMOS parts, and CMOS in general does not draw much power. So a real quick tour of what the layout is. These chips on this corner down here, this one, this one, this one, this one, this one, and this one, are the timing state machine. There's a clock oscillator, 3 counter chips across the top, and an output 8-bit latch for the memory chip. And what it does is it's simply like, think of it as a piano roll on a player piano that has 8 keys. And so the counters simply run. They start at 0 and at memory address 0, and it starts pumping out the pattern. The latch is because the output of a memory that you're just changing the address on very quickly will be glitchy, so I reclock the output to remove glitches. So that comprises the entire state machine. One of the output bits ties back to the reset bits on the 3 counters, so that they, when the thing reaches terminal count, which I don't remember in exact number, it's a little over 360,000 counts, they reset and start again. And in this case, we're running a 4.096 megahertz oscillator, which is divided to get down to 12.5 hertz, the frame frequency, so that this chip can generate all of the pulses in a frame of video, of NBTV video to be specific. Pretty clever, eh? Then these 2 chips here are a I2C parallel port connected back to the Arduino, which provides the frame number. We'll get to that in a second. And another latch for synchronizing, and it will be fired by the frame pulse, the same reset pulse. Excuse me, this is the latch. This is the port. This latch will latch once per frame so that the picture switches between frames. That way you don't get a picture that's half of the last picture and half of the next picture. We will not get any frame breakup, so that synchronizes the port changes with the internal video. These 2 chips are the address count for 1 frame of video. 1 frame of video is 2048 bytes, which just loops. This output port makes up the rest of the address bus, providing the 8 upper lines, so that these memories over here each contain 256 frames. This one contains red frames, this one contains green frames, and this one contains blue frames. Okay, and they're all in parallel. So picture 0 has its red, green, and blue frames at address 0, for instance. Again, these memories are latched. There's 3 8-bit latches that come out. There are 3 8-bit digital to analog converters. And over here, there are 8 op-amps that take care of the business of buffering the output of the D to A converters. And there are a couple left over to proportionally sum the red, green, and blue analog signal from the 3 DACs into a synthesized luminance signal with sync. So there will be 4 outputs. There will be red output, green output and blue output without sync pulses, and the fourth output will be luminance video with sync. In other words, a monochrome NBTV signal. So this can drive both black and white and color televisors. So now let's get on with wiring up the 5-volt power, shall we? Okay. It's my standard wiring technique that you've all seen before. If you haven't, go watch the other videos. Alrighty then. Alright, we're all good to go. Make sure we're still in the frame. Column 1 is wired. Column 2 is wired. Column 3 is completed. Four columns. Whatchamacallums? Column 5. One to go. There we go. So now we got 6 columns wired, red wire. Now we'll connect them across the top and then tie the midpoint to the 5-volt regulator, completing the 5-volt power circuits. It's that fast. All right, let's put in this horizontal wire across the top there. Alrighty, lab guy. So we got 1, 2, 3, 4, 5, 6 columns, and we will call this point the center. We'll call the ROMs the center. So, very good then. We'll tie all these together. Who are you trying to convince, lab guy? Shut up. All of our splits are done. I don't know if you can see the wire or not. Alright, now we just tack her in. If these other wires will jump off. Nope, stayed, oh, one of them will jump off for sure. Very good. To reach their life's goal of being connected to something. Ow! What else could it be? Ah, the smell of burning skin in the morning. Is there anything better? Yes! Yes, there is. Alright. Not too bad. Can you still see, or am I walking out of the frame? There it is. And that other wire jumped off. It's still connected though. I'm not going to fight it today. There we go. They are connected. All right. You can see the wiring across the top. Now the last one ties the regulator in, ground out. So out is closest to the harness. So we go from the output pin over here and to our center pin. And that should be enough right there. And in fact, I'm going to go the other way to the back to the regulator. Our primary power line feeds the center of the distribution matrix, which spreads out left and right and down like a comb. And here we go. Pull him up there like that, straighten him. Thus, bend him in. Like that. There we go. Cool. And we solder him to the capacitor so that he's coming off of the noise filtered point. Just like that. We are there. It is fully connected. So there's the wiring harness for you to admire. Feel free to emulate this method. Okay, 5 volts is entirely connected. So the next connections will be the plus and minus 12, which will feed, plus 12 will feed the 5-volt regulator, and it'll feed these 2 op amps here. So we will be placing the power connector for that up in this region here. It's a 3-pin power input connector for this board. Alright, let's get on with this power connector and get this done. I use this stuff, I call it bulk header strip. I call these headers. Some people call them DuPont pins or Molex pins. If you buy them in bulk, they have an indent that allows you to snap them off. So let's count 3 over. There's our 3-pin connector. And then it's a case of aesthetics. and practicality, of course. Where should it be? Right there. It is placed on the board so that the connector that goes on it will clear the standoff if there's a standoff on the finished board. Probably not, probably a screw head, but it could be a nut. And that's where that goes. If I turned the board over right now, of course it'd fall right out. Scotch tape is your friend. There we go. I've Scotch taped him in place. Flip him over and we solder one pin. Why one pin? The reason we solder one pin is because he's not fully seated and he's crooked. So now we use our fingernail to push him into place and straighten him out. So now those three pins are level left to right and forward and backward. Now we solder the rest of them. Now, just like the regulator, the voltages are on the two output pins and the outer pins, and the ground is on the central pin. So I'm going to put the bypass capacitors on there, and then ground the center. Do that one. That one wanted to get away. Okay, he's in. Then we'll tag him to the, that's not straight. I mean, there's no excuse for not doing your best work possible, right? Be over soon. Ah! Sometimes this can be difficult. Okay. All righty. Now, we run our ground wire. Don't know if you can see it, but I've just grounded, well, put a ground wire to the ground plane at the center pin. Now the tail of it's still sticking up on the back, and we'll tie it to the central point back here. And what I do is I flood over that center pin so that the solder forms a heavy trace for ground. So our ground is now installed. Alrighty, moving right along. let's run our orange wire down to our plus pins. Oh yes, it also goes to our 5-volt regulator. Let's run that one first. Connecting the input side of the 5-volt regulator right now. There we go. Coming back. Then we're going to put a 90-degree bend right there. Beauty. Pin 4 of the op-amp chip. For the curious, that's a TLO84 op-amp, quad op-amp. This board has 8 op-amps in the circuit. Plus 12 volts is wired in orange. The orange goes back in there, and violet. Violet! Violet is our next color. Violet. Or purple. Okay, it only goes to the 2 op-amps. Once again, I cut this neat little notch which the wire locks into. That way I don't end up with this all unspooling all over the table. Alright, let's do our measuring thing. Tweezers. Uh-oh. Pre-strip a couple of inches. 3 or 4 centimeters. A half a cubit. No, half a span. Some other. don't you want to slide? There we go. Out of the picture, am I? There we go. Just like that. And back into the bin. Okay, so we have all of our power lines installed. So lab guy, why do you do all the grounds and power first? Well, if you stop and think about it, all of your chips, their power and ground pins are not going to change. If you got that right on the first time you wired them, those are permanent. Now the signal wiring, like control lines especially, you might need to rework those later and move them around and change them. So if we were to save the power for last, we would have this net over the top of our other wires, making it hard to rework those wires. So I put in the grounds first, which are soldered directly to the bottom of the board. I don't know if you can see under the sockets there, but I soldered these ground pins of the machine pin sockets directly to ground plane. This does two things. It makes the ground of that socket extremely robust. That is a good ground. Solid ground plane, good ground. Second, that pin underneath becomes the tie point for the logic control pins for that chip that I might need to tie low. Conversely, if I need to tie a logic input to a permanent high, I tie it to the power line. So the chip automatically comes with a reference low pin and a reference high pin for programming setting pins. Very, very neat, and you don't end up with your settings wires running over other chips. And every chip is programmed, if you will. So let's say it has 3 pins, like the I2C chip, which has 3 pins you program high and low in various combinations to set its I2C address. So it has the power and the ground pin right there for a convenient point to tap to. And only signal wires run between chips. And power lines, obviously. And that's why I do the powers and grounds first. Also, if you look super close where these power lines join the chip, you'll see a little 0603 capacitor at every location. Those are the 100 nanofarad high frequency noise bypass capacitors, which I use religiously on every single power connection of every single chip. This board now has 2 10 microfarad capacitors, one at the power input and one at the regulator, putting 20 microfarads of large capacitance filtering on the 12 volt line and 10 microfarads of filtering on the minus line, which is on the minus line over here, which is okay because it only has 2 op-amp chips on it, so it's not as heavily loaded. And that's the reason for all of that. I hope you enjoyed this part of the project. Wake up! Alright, I hope that last section there didn't put you to sleep. If it did, I'm sorry. And if you didn't want to get woke up, I'm sorry. Okay, so that concludes the first installment of the 10-4 Eleanor RGBY signal generator. And hopefully every couple of days, every 3 days, there will be another video. So hang in there. We'll get this thing done soon and see how it looks on the big televisor and on the cathode ray televisor. So until next time, this is Lab Guy saying, Lab Guy out.